coming midterm, okay, it will be an open book, which means you can bring whatever you want to the exams. You can bring textbooks. You can bring your own notes. You can also even bring copies of other people's notes. Okay, I don't care, okay, as long as they can help you. Because in real life, as an engineer, those materials are all available to help you to solve real world problems. But there is one thing you cannot bring, that is your mobile phone. You cannot use tablet either, all right? Because with those electronic devices, you can always, I wouldn't say you, people can always go to the internet and search for solutions, okay? And that's, of course, is not fair, all right? Okay, because here, what we want to do is to train you as a real engineer. If you, during the exam, if you go to the internet or go to the large language model for solutions, that is not helpful for our training, okay? All right, any question, okay? If you have any question whatsoever about exam, ask now, because in private, I won't answer any question regarding to the exam, because any information relevant to the exams should be shared in public, not in private, okay? Allow me to speak this in Mandarin, okay? 所有问的问题就是公开问，私底下不回答。The only statement I made is that all the questions about exams will be answered in public, okay? Don't come to see me ask for personal answers, okay? I won't do that because, as I said it several times, any information relevant to the exams should be shared with everybody, okay? Should be shared in public, all right? Okay. It would consist of basically two parts, true and false, and multiple choices, all right? That's it, okay? It will all given in English. So if you want, you can bring a dictionary with you, okay? To help you understand those English, all right? Now, please allow me to remind you, bring your own scientific calculators, okay? You probably will tell me, hey, of course I'll bring my own calculators. What do you have to remind me about that, okay? Because from time to time, people during exams ask me to give them limited calculators, okay? Or ask me if they can borrow calculators from other people, okay? That's not nice, okay? All right? Okay, any question about the next exam, okay, which will be held next week, Wednesday, from 9:10 to 12 o'clock, okay? So, all right? Okay? All right. One thing is for sure, okay, that is, I have no intention to flunk any people in this class. That is not my intention. On the contrary, my basic purpose, my basic goal is at least, I hope, half of you will get a grade higher than at least A minus. Hopefully higher, okay, at least 50% of them, okay? I wouldn't say I'm very generous, but okay, but if you can pass this class, I want to get you good grades. That's my intention, okay? That is really what I want to do, okay? So, okay, bear this message in mind, and hopefully you think it is worthwhile for you to work harder for this exam. for grades, but more importantly, for what you can learn from this class. Okay. All right, let's go back to Newton's law of cooling. Okay. Now, this is the first order differential equation we set up based on the Newton law of cooling. All right. Now, from a control perspective, we chose the T temperature as the output variable, where the surrounding temperature TA is the input. With such arrangement, this differential equation can be rewritten as this, right? So apparently, this is a first-order linear time invariant system in continuous time. Okay, and it can simplify it as this. Okay, now next, what we want to do is we want to solve this differential equation. Now here we want to use Laplace transform. Why do we want to use Laplace transform? Because by using Laplace transform, we can easily distinguish zero input response from zero state response. All right. Now here, initial condition, let's assume is t 0. Okay. By taking Laplace transform of this term, I have this. Taking Laplace transform of this term, I have this. Similarly, for the right-hand side of the first-order differential equation, the x-domain representation is k times u. Now remember, my goal here is to find the response of the temperature. Therefore, I need to solve for y, okay? After rearranging terms, this equality can be written as this. After solving for y's, this is what we have, okay? Here, it is very clear. This is the part of the zero input response. Why? Because input is, input is here. By contrast, initial conditions is here, right? So this element represent zero input response in the x-domain. In comparison, this element represent zero state response in the x-domain. Now, by taking inverse Laplace transform of this term, what I will get is zero input response, which is now T0 times e to minus kt. Similarly, by taking inverse Laplace transform of this term, this is what I will get. Okay. Remember that u of x is a step function, okay, with a magnitude of TA, all right? Because it represents the surrounding temperature, which we assume is always a constant. Therefore, surrounding temperature can be modeled as a unit step function times the surrounding temperature TA. So y of x in the x-domain is actually this term by taking the inverse Laplace transform of z of x, and by using what we reviewed in last week, the techniques of partial fractional expansion, this then can be divided or decoupled, broken into these two parts. Now, by using the technique of partial fractional expansion, we can determine the values of a and b to be 1 and minus 1, okay? Once we have the value of a and b, we have the zero state response, solution for the zero state response in the x-domain. And by using Laplace transform table, we note the inverse Laplace transform of these two terms to be TA and TA times e to minus kt respectively, okay? So the total response, of course, is the sum of zero input response and zero state response, okay? This is the zero input response. This is the zero state response, Okay, now this part comes from, again, initial conditions, initial temperature. Okay, and this part comes from the surrounding environment. Okay, no wonder this is what we call zero input response, and this is what we call zero state response. Okay, now we can simplify this representation by collecting common terms. Okay, this term and this term have a common term, e to minus kt. So this result can be rewritten as this. Okay, now once we have such a representation, we know that this part is what we call natural response because it comes from the pole. It is determined by the pole of the system because it is made of the mode of the system, okay? And the remaining part is what we call forced response. Forced response. Remember that forced response is the result of the input, but it is not the total consequence of the input, okay? Because the total the response due to the input is actually this, not just this, all right? Okay, now for this particular problem, this natural response is actually the transient response system because by definition, transient response is the part of response which will die out as time goes to infinity. And this is exactly what happened to this term. And similarly, when time approach infinity, what is remained in the total response is this constant. So TA is the steady state response. And this is something we expected, right? Because eventually the temperature of the T will be the same as the temperature of the surrounding environment. Okay, now for the first order system, there is a very important parameter for control system in the context of control system design, which is time constant. All right, now to illustrate the idea of the time constant, let me first summarize the result that we have. This is the total response, made of zero input response and zero state response, also made of the sum of forced response and natural response. Let's just assume that the initial temperature is 0 degree and the surrounding environment, the temperature of the, that is the ambient temperature is 100 degree for the sake of simplicity, okay? So it's no longer a cooling process, it's actually a heating process because eventually the temperature will rise from 0 to 100 degree, okay? So it's no longer a cooling process, it's a heating process. But the Newton's law of cooling is still applicable because heat loss, no matter it's cooling or heat, heat transfers, no matter cooling or heating, okay, is always proportional to the temperature difference. Now, with T0 to be 0 and TA to be 100, this result can be rewritten as this, all right? Okay, T0 is 0, okay? So this go away. What we have is this term and this term, okay? And this is what we have. Now, the constant in this case is defined as 1 over K. Remember, K is what we call cooling coefficients, okay? So, how is, let me go back to the definition of cooling coefficients, okay? What is cooling coefficients? Cooling coefficient is a very important parameter for the Newton laws of, for the process of Newton law of cooling, all right? Now it is, we know that based on the Newton law of cooling, heat loss is proportional to the temperature difference. But proportional to what? But there is a constant of proportionality, and that constant of proportionality is k. So that means the larger the k is, the fast the faster the heat cooling process is. Okay, k is faster. This derivative is larger. Therefore, the faster the cooling process. All right. Now, 1 over tau. Tau is actually 1 over k. Okay. Now, by introducing or by defining tau as 1 over k, this representation can be rewritten as this. Okay. Now, let's assume this so-called tau, which is defined as the time constant of this photovoltaic system, to be 5 minutes. Okay. So this equality can be written like this. And by using your calculators, you will see that when T equals to tau, temperature is actually 63.2 degrees. When T equals to 2 tau, the temperature is 86.5, etc., etc. So what we can see is that in engineering, we often say 1 tau correlate to 93.2% of total change down, right? And 2 tau represent 86.5% total change down, okay? And so for most practical purpose, the system settles in about 4 to 5 time constant, okay? System settles in about 4 to 5 constant, okay? So if the tau is larger, then the time required to settle down is longer, okay? Let's say its tau is 5 minutes, then it will take the system 25 minutes to go from 0 degree to 99.3 degree. But if tau is no longer 5 minutes, my constant now, my time constant is now 1 minute. Then it will only take 5 minutes for the system, for the temperature of the system to reach 99.3 degrees Celsius. Okay, 25 versus 5. Okay, the only difference is that for this part, tau is equal to 5. Okay, and for the other part, tau is equal to 1. So tau actually characterizes the speed of response of the system. That is the reason why we call tau the time constant of a first order system. All right. So let's put it in written text. Okay. Time constant in control systems. The time constant of first order system is a measure of how fast the system responds to a change in its input. It is defined as the time required for the system output to reach 93.2% of its steady state value. Okay, right? Okay. One time constant of time accomplished 93% of steady state response. Okay. Now speed. A smaller time constant indicates faster response. By contrast, a larger time constant indicates a slow response. Okay, so time constant, therefore, is a very good measure of the speed response of the system. A system with large time constant may be more prone to instability. Okay, keep this in mind. Okay, I cannot prove it now, but I can tell you why. Why is this the case? Because a larger time constant means a slower system. A slower system means the system might not be fast enough to react to changes, okay? It cannot perform necessary correction to the system output in time because it is simply too slow, okay? Right? So to put it in perspective, let's say a man really have to react to a difficult situations fast enough. Otherwise, before I can put anything in motion, the thing's already gone out of control. All right. So the speed of response, of course, has everything to do with the stability of the system. All right. So larger time constant, slower response, and therefore worse stability. Okay. Now this is a figure to show you how the response curve look like. Okay. Now here I want to emphasize one thing. From this result, you will see the response curve is actually made of an exponential function. Okay. Okay. This is exponential function. Okay. This is an important result. Why it is important result? Because when it comes to exponential function, when we first learn exponential function, I think you probably have the same question as I have. I don't know why do I need to deal with an exponential function such as this, because I don't see exponential function when I go to supermarket for shopping. I don't see I need exponential function when I receive my paycheck. I don't see it in my daily life. But here, it tells you that Newton's law of cooling describes a very, very common natural environment, which we will probably encounter every day, right? Cooling, heating. Yeah, we see that all the time. And if you want to describe how the temperature changes with time during this process of cooling or heating, you need to use exponential function because that's how the world operates. OK， 所以指数函数为什么很重要？那就是因为真实世界就是这么运作，好不好？哦 ，OK， now the next thing I want to do is to relate the pole location and the speed of response and the time constant. Here we have a first order system, just okay. Now Rx is the input, C of x is the output, G of x, which is A over x plus A, is the transfer function. Apparently the pole is located as minus A, all right? And the time n, by taking inverse Laplace by taking the inverse Laplace transforms of this equality, we find a state response of this system. Okay, no big deal because we just solve a problem which is identical to this problem. Okay, now here in this particular case, 1 over A is the time constant, right? 1 over A is the time constant. So what you see is that what do we want to identify here is that we want to identify the relationship between the location of the pole and the speed of response of the system. Okay, the pole of the first order system is located at 1 over tau, right? Because here is minus A And we know that 1 over A is the time constant. So the first order system, the pole is located at 1 over tau. If the pole is closer to the origin, okay, that means the system responds more slowly. Why? Because it is close to the origin. In this case, tau is larger, right? Okay, the distance between the pole and the imaginary axis is, of course, A, right? And we all know that tau is 1 over A, because 1 over A is the time constant here, okay? Now, if the pole is closer to the origin, which means A is small, okay? Let me put it this way. If pole is moving closer to the origin or to the imaginary axis, then A is becoming smaller. In this case, since tau is the inverse of A, or 1 over A, therefore tau will become larger. And therefore, a larger time assessment with larger time constant indicate slower response. Therefore, session will become slower. Okay, so this is the reason why that the pole of the first order system is located at minus 1 over tau, and if the pole is closer to the origin or to the imaginary axis, the system responds more slowly. By contrast, if the pole is further from the origin, further away from the imaginary axis, the system responds more quickly. All right? Okay. So this is the very first time we identified the impacts of the pole location on the performance of the systems. Okay. All right. Okay. This is the very first time we tell you how pole locations impacts or influence the performance of a control systems. Okay. So the location of pole matters. Okay. This is the reason, also one of the reasons why the transfer function is important, because with a transfer function, you can readily identify the location of poles. All right. So the distance of the pole from the imaginary axis impact the speed of response and stability. Poles further away from the imaginary axis result in faster decay and generally more stable system. Okay, keep that in mind. Keep that in mind. Keep that in mind, because if we know this is the truth, then in designing a control system, we know where to put the poles, where to locate the poles, and that become a guideline for controller design. Okay, now let's see the impact of pole, the location of pole on the speed response, as well as the steady state error of a first order system. Again, this is the first order system under consideration. Okay, represented by a transfer function 1 over Ts plus 1. This T is actually, think of it as tau, which is time constant, because in this case, pole is located at 1 over tau. Okay. Now, here, what we want to study is unit ramp response, which means my input here, CT, is actually T. Okay. All right. I'm sorry, not CT. My input RT is actually t, a ramp function, all right? And the Laplace transform of t is 1 over x squared. Therefore, the unit impulse response for this first order system is 1 over tx plus 1 times 1 over x squared. Now, this term can be written as this, okay? Now, by breaking this term into 3 simpler terms, and then we can take each of these 3 terms by inverse Laplace transform. And this is what and this is therefore the unit ramp response for this first order system, all right? So let's collecting terms, okay? I'm sorry. Let's now study the arrow. The arrow is actually the difference between the input and output, because here input RT is actually, where is it? Okay, I'm sorry. The input here is actually the target output. Okay, I set that input as the target output, and hopefully, if everything goes well, the actual output of the system will be the same, or at least track the target output. Okay, of course, this is not a perfect, this is not always the case. Therefore, here, we want to study the arrow, output arrow, okay? And the output arrow is defined as the difference between the target output and the actual output, all right? And since we already know CT is this, and we already know R of T is this, therefore, this is my output arrow. And when T goes to infinity, this term vanishes. So this is the steady state arrow of the system, okay? Here, the steady state arrow, as you know that T is actually tau. This is the time constant. So for the unit ramp response of a first order system, you see that the steady state arrow is actually equal to the time constant. So the faster your system is, the smaller the time constant. But let me put it this way. The smaller the time constant leads to 2 important consequences. The first is the smaller the time constant, the faster the response. The second thing is the smaller the time constant, the smaller the steady state arrow. Why is this the case? Because the faster the system is, the system therefore become more capable in tracking the fast changing target output, because the target output is changing. It's not a constant. It changes with time. In this particular case, it actually increased linearly with times. So the system really have to run after this change and hopefully can catch up. But in order to catch up, the speed of response of system has to be fast, okay? And in this particular case, this is the target output because this is input, which is a ramp signal. And this is C of t, which is calculated from this expression. And you will see that there is always a gap between desired output and the actual output. And when time goes to infinity, this gap becomes a constant, which means after a while, the arrow just remains to be the same. It will not go away. It will not decrease with time. This is the reason why we say that there is a steady state error. And the important thing is for the first order system, that let me put it this way, for the unit ramp input response, for the unit ramp response of the first order system, this steady state error is actually the time constant of the system. And this should tell you that why the speed, this should tell you that speed of response of the system really is important. It really matters. If you really want to have a fast response, a system of fast speed of response, okay? Now, we can also determine its unit impulse response by taking the inverse Laplace transform of this representation. And this is what it will look like, all right? As you can see that as t becomes smaller, this curve will decay faster. So unit impulse response can also tell you a lot about the speed response of the system, all right? Okay. Now, why do we care about unit impulse response? The reason why is unit impulse response in many cases, especially for mechanical systems, can be experimentally determined. If it can be experimentally determined, then let's say this is the experimental results of a first order mechanical system. Then from this curve, which is obtained from experiments, I can readily determine its time constant. Once I know the time constant of the system, I know everything about this first order system, because first order system only have one unknown parameter, that is the time constant. With time constant known, I know where the pole of the I know where the pole is. I know the impulse response. I know its step response. I know its zero input response. I know its zero state response. I know everything. All right? Okay. Provided that initial conditions are also given. All right? Okay. Wrap it up. Okay. That wrap up our discussions for first order system. Let's move one step higher to second order systems. Okay. Now, there are several topics we want to address here. The first is related to spring mass systems. Remember, not spring mass damper system. Okay. We are not ready to jump into spring mass damper system. We are only considering spring mass system. We will leave out the damping effect for the time being. And then we'll study simple harmonic motion, which I believe you have learned before in your high school physics course. And we'll talk about one of the very important parameters for the second order system, which is natural frequency. Okay? Now, before doing that, let's talk about the idea of equilibrium positions. Let me give you an example first. Okay? Let's say this is a spring. Okay? Originally, when unstretched, the length of the spring is L. When unstretched. Now, let's attach a mass to the spring. Hook it up, okay? And due to the gravitational force, the spring will, the length of the spring will extend, okay? And the amount of deformation, let's say, is S, okay? Apparently, mg is the same, is equal to Ks. K, of course, is the spring constant of this spring, okay, or the stiffness of this spring, all right? So, in this particular equilibrium positions, the gravitational force, the gravitational force has been balanced, has been equalized by the spring force. And therefore, this position is what we call equilibrium positions. And then we will set up a coordinate system to describe the displacements, to describe the movement of this mass. Now, instead of this 1D coordinate system, we need to specify two things. First, the origin. Second, the direction, all right? The origin apparently is chosen as this equilibrium position. So this position is set up as S equal to 0. And we assume downward direction. That is when the spring is stretched, is the positive direction. By contrast, when the spring is compressed, the mass is moved in the negative direction, all right? So that is how we set up our coordinate system for the spring mass system, okay? Remember that the origin or the position of the spring mass system is located at the equilibrium position, which equilibrium position is defined as the state of the system where it tends to stay unless disturbed by external force, okay? So once you attach the mass to the spring, and the spring will have some deformation, and once it comes to the equilibrium position, it will stay there forever, okay? Now, here, we want to set up the equation of motion for this spring mass system. Okay, again, let's apply Newton mechanics, okay, Newton's laws, which tell you that m times a, of course, the double derivative of x, okay, and summation f should include all the external forces, which include gravitational force, which include spring force. Since the total deformation is S plus K, therefore the spring force is minus K times the sum of S and X, okay? And since we know that mg equal to Kx, that is spring force, balance or equalize gravitational force, the only external force left is minus Kx. Therefore, the equation of motion becomes this, okay? Or I can rewrite it as this. Or I can, again, rewrite it as this, where omega squared is defined as K over M, okay? Remember, K is the time constant. M is the mass, okay? Another way to look at it is K is the stiffness of the system. And in comparison, M represents the inertia of the system, all right? Now, omega here is defined or called as the natural frequency of this spring mass systems. The reason why it is called the natural frequency of the system is that it is the frequency at which a system would oscillate if there were no driving or damping forces, okay? So here we have a spring mass systems. If let's say it have an initial velocity or you have an initial displacement and you release the mass, and then the mass will oscillate up and down forever. And this kind of motion is what we call simple harmonic motion, right? And this simple harmonic motion, it does not just oscillate in an arbitrary manner. It oscillates with a fixed frequency. And that fixed frequency is the natural frequency. All right? Okay. Now, so the larger the omega is, the faster the oscillation. All right? Now, let's go to the definition of the natural frequency. Here, how do you have a higher rate of oscillation? Two possibilities. One, you increase stiffness. Okay, that makes a lot of sense, because if a spring is soft, you stretch it and release it, it will go up and down, but not in the very rapid fashion. By contrast, if this time constant, the spring constant is very large, you have a very stiff spring. Once you stretch the spring and you release it, it will go up and down, very, very fast. Okay, so increase the stiffness will increase the natural frequency. Right. Now, M, however, act in exactly the opposite way. Okay. Here, if M is one, make the mass go up and down. Of course, here you only have two things. One is spring, another is mass. So the only reason the mass will go up and down because it's due to the spring force, right? It's due to the spring force, all right? So, and the spring force is always proportional to spring constant. Let's say the spring constant is fixed, and therefore the spring force is therefore all fixed. And with the same spring force, when M becomes larger, that is when the spring have to move a mass which is heavy, then it is difficult to move such a mass in a very, very rapid fashion. By contrast, with the same spring, with the same amount of spring force, if the mass is very, very small, okay, then using the same spring force to drive a small mass, it is really a piece of cake. You will get very large acceleration and deceleration, right? So apparently that will result in very fast acceleration, okay? So that is the reason why natural frequency is inversely, the square of natural frequency is inversely proportional to mass, because the heavier the mass, the more difficult to move the mass, okay? All right, now, so compact system may have multiple natural frequencies, okay? What we have is a spring mass system, which is a second order system. If we have to deal with a higher order system, let's say fourth order system, eighth order system, then the system probably have multiple degree of freedom, and each degree of freedom may possess its own natural frequencies, okay? Now, and each natural frequency corresponding to different modes of vibrations. So in that case, you have different modes of vibrations, okay? In real system, damping is usually present, okay? And with damping will affect the observed frequency or oscillation. So there are two kinds of natural frequency. One is what we call undamped natural frequency, okay? Natural frequency of a spring mass system. And we also have damped natural frequency. That is natural frequency which you have to take damping ratio into consideration. Okay, now controllers are often designed to avoid exciting the system at its natural frequency. Why? Because we want to avoid resonance, okay, which we will talk about in a few minutes. Okay, it's 11 o'clock. Let's take a 10 minutes break, okay? Thank you again for your participation and patience.